Welcome back to the lab. Today we're going to test our UPS's ability to detect and respond to a power failure. We're going to brown out, interrupt, and cut power to the DC inputs of our UPS to see how it responds. We want to see some crazy stuff happening on the input. Relays clicking, madness everywhere, but no interruption on the inverter output. Now, this video is all about timing. Our goal was to implement a circuit capable of switching over from a primary power input to a secondary power input with 0 milliseconds of dead time. None. No interruption on our sine wave output. And that's a tall order. As we were designing this subsystem of the UPS, the one responsible for actually flipping power over from one DC input to the other, we hit a bit of a roadblock. See, while we wanted to use some transistors to switch power, it was actually a bit of a problem. When used normally, the body diodes in our switching circuit would allow the voltage source not being used, either the battery or the main DC input, to feed virtually unlimited current to the lower voltage source. That's a bit of a problem, because our batteries are normally sitting around 24 volts. Our DC input can go down to 12. Yikes. That would be a problem. Thankfully, we caught it during the design review cycle and it never made it on a board. Not only would that design have not worked due to the body diodes, the extra losses in the UPS, due to using two back-to-back N MOSFETs as a mitigation, would have made them too lossy for our application and even more expensive. Dang. There's just no real easy way to win here. The series of compromises and failed designs that followed eventually got us, well, here. We landed at an architecture that still has two low voltage DC inputs. These inputs are switched by relays, which are then fed to the push-pull converter. This can work, but we need to be very careful. We need to be careful that whenever the relays switch, the current flowing through the relays are small. Now, this is a big ask considering that our UPS is designed to have 700 watts flowing through the converter at all times. Ultimately, I think that our implementation for phase one, this first iteration of the design, made a lot of compromises, maybe even borderline too many when it comes to timing. If I'm being completely honest here, I think that a little part of me was afraid to implement the architecture that I knew to be best, because the architecture I think will function best is the architecture that requires the most transistors touching high voltage. I'm feeling a lot more comfortable with this now, but we'll get to that in a couple videos. Regardless of why, here's where we ended up. The relay operation time is about 10 milliseconds. In order to keep the inverter running for 10 milliseconds plus soft start time, approximately another 100 milliseconds or so, we need 77 joules of energy stored somewhere inside the UPS ready to go. That's a lot of energy. With only 80 microfarads of bulk on the high voltage side, we can store 5 joules there. The couple millifarads on the low voltage side can store an absolute maximum of 4.5 joules in the 40 volt input. Something just doesn't add up here. If we need 77 joules to ride through the crossover period, but have 9 joules stored in the UPS, only 2/3 of which we can actually use before browning out, yeah, I can tell you before I ever put an oscilloscope probe or a multimeter on this board, we're going to have trouble. That said, the trouble we're going to have will be the UPS dropping out for a short while, not welded relay contacts. We're trading big trouble for little trouble. In a way, I wrote the firmware running on our UPS to ensure the current through the relays will be as close to 0 as possible before they change position, not to optimize for 0 off time. There's certainly room to tighten up the timings involved with this transition, but the reason why we don't just throw the relay from one position to the other is because switching relays carrying DC while loaded can cause excessive arcing. Contacts can weld together, but in general, switching relays under load will cause them to break much faster whether AC or DC is switched. Right then, enough chatter. I've told you that I don't expect our UPS to do very well during this test, and I've told you why. I guess we can all go home then. Thanks for watching. Nah, just kidding. Let's see how well our design does. Let's see if it really performs in the lab. Let's see if the design really works. After all, I may be pleasantly surprised at how quickly the UPS can transition from one DC input to the other. I may not. So here's one big issue right out of the gate. With the way our first prototype UPS schematic shook out, we never really connected the ADC pin from the microcontroller to the primary DC input. What I'm trying to say is, our UPS can't detect when power has failed until it's failed. We can detect when the push-pull converter fails to regulate, But it's too late by then because we've already burned all the power stored in our output capacitance. We need to know right away. How can we run our test then? Well, let's pretend, if only for a moment, let's pretend that the primary DC input is really the secondary DC input and vice versa. We'll drive our decisions around whether or not to switch based around the absence or presence of battery power, and assume that the other DC input exists whenever that main input does not. By tweaking our software in this way, running some logic around that whole situation, we can clearly see, well, I can't see anything. That's weird. New firmware? Maybe it's a software issue. Okay. Nope. It's not that. Well, let's look for a hardware failure then. I mean, it's always possible. The circuit's pretty simple, so the debug shouldn't take long. It's literally the microcontroller pin, a BJT, and a relay coil. So let's measure the voltage on the base and collector of the NPN transistor that's tasked with firing this relay. Well, the base looks okay. It's only 0.7 volts. We're at least trying to turn on the relay, so that's good. What about the voltage at the collector? Well, I'm seeing 5 volts here. The relay is driven with 12. We're trying to drive it to 0. Right then. I would expect to see something a lot closer to 0.3 volts if we were successfully turning on the transistor the way that we intended. After all, our intention is to drive this BJT like a switch, not like an amplifier. We're meant to drive it into saturation. So the fact that we're seeing 5 volts, not 12 and not 0, smells like a case of insufficient base drive. Allow me a short tangent about base drive, and it's really important. Base drive is critical to consider when using a bipolar junction transistor as a switch. Base drive current is the current flowing from base to emitter in a BJT, and analyzing whether this drive is sufficient for a particular transistor is called drive analysis. Drive analysis and base drive are so critical for BJTs because they're current controlled devices. Unless there's another element in the circuit that's limiting your maximum current, the collector current will be equal to the base current multiplied by a proportional factor. This factor can be called beta or HFE. Unfortunately, beta isn't constant. Beta can depend on temperature, age of the device, and the quantity of current being controlled. In this case, our DC current gain when controlling 100 milliamps of collector current with the SOT23 MMBT3904 transistor is rated at 30. Let's apply this factor to ensure that our circuit appropriately drives the relay. The relay requires 100 milliamps. When this is divided by 30, that beta factor we were just talking about, just pulled out of the datasheet, we'll find that 3.33 milliamps of base drive is required at a minimum. Our circuit uses a 10K resistor driven with 5 volts, which can provide no more than half a milliamp of base drive. I'm choosing my words carefully here because we've neglected the base emitter voltage drop in this quick calculation. In this unrealistically optimistic calculation where the base emitter voltage is 0, not 0.7, our circuit can provide 1/6 of the current required to drive the base of our BJT. This means that instead of behaving as a switch, we're accidentally operating this BJT in the linear region as an amplifier. Whoops. The current-dependent switching effect is one reason why an engineer might use a different topology or technology for switching applications like this. MOSFETs are similar devices in the sense that they're transistors, but they are inherently voltage controlled, and using a voltage controlled transistor to control current, the base drive current requirement's removed. This is sometimes very important because microcontrollers have a single pin and a total package current output limit for GPIO pins. If you have a micro with 300 pins, you might run into that limit if you're requesting a milliamp or 2 out of every pin. We aren't up against this limit here, and we're only switching a couple things, so I think a BJT will be fine for our application. We just need to drive it a little harder. That's some solid theory. Let's jump into the lab to see how I confirm this hypothesis in real time. R87, that's a 103, so that's a 10K, so we're driving it with half a milliamp. Oh, that just might not be enough to flick the relay over. Let's do a little social experiment here. 10 volts on one side. Okay. 100 milliamps is what we require. You know what? It looks like that actually has enough holding power to hold it. If I am very in the way, aren't I? So now that it's in, we're able to hold it. If this drops, just doesn't have enough oomph to pull it in. Oh, we can fix that. We can give a BJT a little more drive. That's an easy problem to solve. Come on now. Alright. Looks good to me. Isn't that awesome? We were able to use our multimeter current mode to latch the relay. Once latched, the base drive was sufficient to hold the relay closed, even though it wasn't enough to close it. That's awesome. Coffin, meet nail. This is easy to fix since our microcontroller can source up to 20 milliamps per pin. We changed our 10K resistor for a 1K resistor, provided 5 milliamps of base drive. Plenty for this application. Now that our microcontroller can actually control the relay, let's try to run our test again. Let's observe the mains waveform as we cross over from primary to secondary DC power input. We're pretty confident that the crossover time would be too long at the start of this video, but will we be right? Was the engineering degree worth it? Do I know what I'm talking about? Let's power on. Let's see if we can fire that relay now. What was that? Whoa. Whoa. That sounds nasty gnarly. Let's give this thing more current. A little more voltage. Not sure why the relay is click-clacking like that. But we're making a sine wave off the secondary DC input. Now we're on the primary input. Alright, here's the real test. We're going to drop this down. Oh, yes. Oh yeah, that was awesome. So what you just witnessed was this thing changing inputs. Okay. What does this tell us? Now, let me refocus the camera. This tells us exactly how long that pulse was when the power was out. I have a feeling it is not going to be pretty. Oof! 1.3 seconds. Oh. Oh, that's so bad. Oh, that's so bad. Let's see if that's consistent. Yeah, that's a 1.3 second power switch routine. I mean, in its defense, nothing blows up. So, you know, all things considered, could do worse. Switch back to the primary input. Alright, so now we can demonstrate this with a live load. So you can see the light bulb, and now we're going to increase. That's the crossover time. It's long enough that the phone could tell that something happened. It's long enough that the kilowatt reset. I mean, it's still probably faster than a generator kicking in, but our requirement was 0 dead time. This is not 0 dead time. This is a lot of dead time. Yes, the degree was worth it. Even though the results of this test, 1.3 seconds of off time when switching sources, is not what I would call ideal, given our requirement of 0 milliseconds, we definitely can switch between the DC inputs and nothing is damaged. I definitely have some great ideas on how to improve this design. Long story short, our UPS is, in fact, a UPS. I'm pumped. If only we could charge these lead-acid batteries somehow. Man, that'd be great. The UPS may not have the output power we'd like. Every circuit may not have worked out exactly how I would have liked, but I think that's okay. When push comes to shove, DC comes in, AC comes out. I'm really excited about how our design has been working so far. We are well on our way through testing our first prototype, but there is still a lot to do. If you want more, consider subscribing to be notified of our future videos where we'll be testing the battery charging algorithm and summarizing everything we've learned about our UPS prototypes so far. I think that today's testing went great. If you like this UPS project, let me know by hitting the like button on this video, finding us on Twitter, or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EE for Everyone, and thank you for staying till the end. Bye!